All right, a quick disclaimer to those of you who aren't taking me for 180. Thermodynamics, I feel, is too large and too difficult a concept to really fit into 170. However, about 50% of the places out there put it in 170, and half of them put it in the second semester. Because some of you are going on to other institutions, what I've decided to do is give you a very, very quick, non-theoretical approach to how to work thermodynamic problems mathematically. In other words, we're really just focusing on the math portion of this. In other words, how to solve those homework problems. If you're going to another college and not taking Chemistry 2 with me, I strongly recommend that you read Chapter 8 on your own at the end of the semester. That having been said, this will provide you all the mathematical tools you'll need to succeed in Chemistry 2, even if you don't take it with me. All right, what is the topic of this chapter? The topic of this chapter is thermodynamics, and that's the study of energy changes and the corresponding changes in matter. Let's define some quick terms here. The first of these is energy. Energy is the capacity to do work. The SI unit of both work and energy is a joule. You are responsible for knowing a joule. You're also responsible for knowing that a joule is a kilogram times a meter second times a meter squared divided by a second squared. Just like you're responsible for knowing that heat wave is something to make note of. Heat wave. Another unit is a calorie. A calorie is another unit of energy, and it's equal to the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. Well, 1 gram of water is a really, really small quantity of water, about the mass of a paperclip. And 1 degree Celsius isn't a large temperature change. So a calorie is such a small unit of energy, it's practically worthless. As a matter of fact, if you grab the nearest food label and flip it over and look it on the back, you'll see that they have a unit there that's capital C calories. Capital C calories is different from lowercase calories. Capital C calories is actually 1,000 calories, or 1 kilocalorie. But for some reason, food manufacturers decided they didn't want the term kilocalories on the back of a food label. So they invented the unit capital C calories for kilocalories. You're responsible for knowing that 1 capital C calorie is equal to 1,000 lowercase c calories. You're also responsible for knowing that 1 calorie is 4.184 joules. You need to memorize that 1 calorie is equal to 4.184 joules. There will be actual homework problems you will not be able to answer in this class without that value. Let's do some quick unit conversions with calories and joules just to make sure we're on the same page. How many calories, lowercase c, are obtained from a pat of butter if it provides 150 joules of energy when metabolized? You're saying, no problem. We did this the first chapter. And you're absolutely right. We have joules here. We're going to place joules where they cancel out. We want lowercase c calories. We know that 1 lowercase c calorie is equal to 4.184 joules. And that's going to give us 36 lowercase c calories. Now, energy, or the ability to do work, comes in lots of different forms. It can be chemical energy. It can be electrical energy. Two of the types of energy that we'll make constant reference to, and you're probably already familiar with, are kinetic energy, and that's the energy of motion. And kinetic energy is equal to 1/2 the mass of an object times the velocity squared. In order to get energy in joules, you have to have mass in kilograms and velocity in meters per second. The other type of energy we often deal with is potential energy, and potential energy is simply stored energy. The energy in chemical bonds is an example of potential energy. All right, let's make sure that we're clear on the concept of kinetic and potential energy. Kinetic energy is the energy of motion. So anything that has motion has kinetic energy. So somebody rollerblading would have kinetic energy. A peanut butter and jelly sandwich. Is a peanut butter and jelly sandwich in motion? No. However, peanut butter and jelly sandwich has bonds, chemical bonds inside it that store energy that our body then converts to potential kinetic energy. So peanut butter and jelly, since it has chemical bonds storing energy, is simply potential energy. Mowing the lawn. To mow the lawn, you're putting things into motion, kinetic energy. The gasoline in the lawnmower's gas tank, however, is a substance with chemical bonds that we burn to unleash the energy stored in those bonds. Gasoline is potential energy. It's stored energy. That's why gasoline is so valuable. If something is valuable, then you know Captain Cold is after it. Captain Cold. What I want you to do with Captain Cold is obvious. The next topic we want to talk about is that of specific heat. In order to talk about specific heat, we really need to define heat. Heat, represented nearly universally in thermodynamics by the lowercase cursive letter Q, is also called thermal energy, and it's heat associated with the motion of particles. A little bit better definition of heat is any energy that flows from areas of high temperature to areas of low temperature. It's important to note that heat is not a type of electromagnetic radiation. We tend to link heat subconsciously with the IR spectrum because our body dumps heat in the form of infrared radiation. Heat can actually be any type of radiation as long as it's energy that's flowing from something that's high temperature to energy that's low temperature. The best way I like to think of heat is just a category of energy. Specific heat is the amount of heat that raises the temperature of 1 gram of a substance by 1 degree Celsius. The specific heat is different for different substances. Specific heat can be represented by the equation specific heat equals heat divided by mass divided by change in temperature. That's not the equation I like to use. The equation I like to use, and the textbook used to use until I think they got tired of people, well, using the obvious mnemonic device for it, is that Q equals, I can't remember. Oh yeah, crap. Right? Heat equals, crap. you should never ever forget the specific heat formula. When we talk change in temperature, it's really important in thermochemistry, and we're going to see this a lot. Whenever you see a triangle in front of a symbol, that's a delta. And it stands for change. And you've actually seen these triangles before if you've had calculus. In math, rather than write the triangle for delta, they use a cursive letter D. See, calculus does come in handy. In chemistry, however, we use the symbol triangle for change. Change in the chemistry world, and it's real important for thermodynamics, you mess up this difference and you're going to mess up a lot of your homework problems. You're always going to subtract. It's always going to be final minus initial. So for our change in temperature, your change in temperature is going to be equal to your temperature final minus your temperature initial. So that is your specific heat formula. I'm hoping you're writing it down. In the SI system, it's not letting me, come on, cooperate. There we go. In the SI system, specific heat has units of joules per gram per degree Celsius. Let me write that better than it's typed there. Joules per gram per degree Celsius. Since we're talking 1 degree Celsius and a Kelvin is the same size as a degree Celsius, you can also write specific heat as joules per gram Kelvin, and they'd be the exact same number. Those two units are interchangeable. Your book and I will also use them as interchangeable. Metric uses calories instead of joules, and in the metric system, your units for specific heat are calorie per gram per degree Celsius, or calories per gram per Kelvin. Different substances have different specific heats. You can find all sorts of tables for them. This is the table, I believe, from your book. It should be the table from one of my textbooks. Make sure you use these values or the values given to you in the problem. In this class, we're treating specific heat like it's a constant. In reality, specific heat changes as a function of temperature. So if you go on the internet, you may see slightly different values for the specific heat for different compounds, based on what temperature basis they were using for the table. I don't expect you to memorize all these. That's a waste of time. Have this table handy. However, that being said, I do expect you to memorize the specific heat of water. You have to know the specific heat of water. Nearly every single homework problem expects you to know the specific heat of water without them telling it to you. So you need to memorize, get a tattoo, do whatever it takes to remember that the specific heat of water is 4.184 joules per gram per Kelvin, or 1 calorie per gram per Kelvin. You have to memorize these as the specific heat of water. And here's a slide I threw in really just to help you work the equation when the time came. I'm going to write it symbolically underneath it here. Crap. Where Q is heat, M is mass, delta T is change in temperature, and SH is specific heat. I use two different textbooks. One textbook does specific heat as SH. You'll also see, and it's quite frankly more common, you'll see specific heat represented by a capital C, which is a generic constant, just generic constant specific heat, which is why I tend to stick to the SH. Let's work an example. How many joules are absorbed by 45.2 grams of aluminum if its temperature rises from 12.5 degrees Celsius to 76.8 degrees Celsius. I like to work these a lot like I do the gas problems. When I'm dealing with a thermodynamic equation, I like to look at this and say, okay, can I identify all my variables? Here, I can see that I have a mass of 45.2 grams. I have an initial temperature of 12.5 degrees Celsius, and I have a temperature final of 76.8 degrees Celsius. And they're wanting to know joules, which is a form of energy, and heat is a form of energy. And we're seeing a temperature change. So one of the things people have trouble with in thermodynamics is kind of knowing what to do. So let's pick apart this question and look for clues. Whenever you read a question and you see a change in temperature, that means that somewhere in this problem, it may just be one part of the problem or it may be the focus of the problem. At some point during the problem, you're going to have to use that specific heat equation because you see the change in temperature. Whenever you see the change in temperature, boom, that's your clue. You're going to use that formula. Well, our specific heat formula is Q... crap, I forgot it. Oh, wait. There it is. It is crap. I know. I'm like a 5th grader, aren't I? I can hear my wife groaning from outside the door. But at any rate, we know our mass. Check. They gave us a mass. Check. They gave us the information to solve for our change in temperature. Check. They're wanting us to solve for our Q. So all we're really needing to solve this is a specific heat. Well, I can go to the internet and find all sorts of different specific heat values. Or I can look at my table, which is what I'm going to do. And the specific heat of aluminum is 0.897 joules per gram per Kelvin. And that's from the table. That's where that came from, right? Came down like Moses bringing down the 10 Commandments. So let's keep forward our substitution. We've got that mass, 45.2 grams. We've got a change in temperature. Temperature final, 76.8 minus temperature initial, 12.5 degrees Celsius. So we have everything we need to solve for our heat, so let's do it. So Q equals 45.2 grams times 0.897 joules per gram per Kelvin times 76.8 minus 12.5. So Q equals 45.2 times 0.897 times the quantity 76.8 minus 12.5 equals 2.607 times 10 to the third joules. And one thing a lot of people question right at this moment is they're saying, wait a second, Dr. Kelly, can we focus on the units for a second? because I'm seeing degrees Celsius here and here, and I'm seeing Kelvin there. How is that working out? How come we're not having to do a unit conversion there? That's a good question. Here's why. We're taking a difference in temperature. We're not taking it relevant, we're not referencing 0. We're taking the distance between 2 points on another number line. And since the size of a unit of Celsius and Kelvin is the same, we don't need to worry about that Kelvin conversion. Another way, if you just want to prove it to yourself purely mathematically, look what would happen if we did do that Kelvin conversion for our temperatures. We'd have 76.8 plus 273.15 minus 12.5 plus 273.15 well, we just wind up distributing the subtraction sign, right? So what we wind up with is 76.8 plus 273.15 minus 12.5 minus 273.15. So we can see that those 273.15s wind up canceling out. And we just wind up with 76.8 minus 12.5, the same thing we would have done had we not done that Kelvin conversion. So since we're not taking it relative to 0, we don't need to worry about the difference between Celsius and Kelvin when we're just taking a temperature difference. All right, chemistry's easy, life is hard. Let's keep moving. All right, this is one of my favorite test questions. I don't think I've ever failed to ask it on an exam for my in-class students. If the same amount of heat is added, what will occur in a substance with a lower specific heat? Okay, let's play two different games in order to answer this question. Let's play the definitional game. Specific heat is the amount of heat it takes to raise the temperature by 1 degree. So the greater the specific heat, the more energy it takes to raise the temperature. That means the smaller the temperature change is going to result. That means you're going to get a smaller temperature change for the same amount of energy. If you think of energy as dollars, you can think of specific heat as the price. If you have $10 to buy food with, do you get more food if you buy $1 hot dogs or if you buy filet mignon? Right? You get more food if you buy the hot dogs or the lower cost item. So the converse of this is also true. The lower the specific heat, or the lower the cost of the temperature change, the greater the temperature change for the same amount of energy. That's one way to rationalize it, and that's how I would prefer to rationalize it. But I'll tell you what, as a student, I love doing mathematical modeling, and it's something, if you've had me in lab, we've already played around with a little on the Boyle's Law lab, in the lab wet portion itself. You can do that in this situation too. We know that Q equals mass times specific heat times the change in temperature. So we set up two scenarios. We set up an object where we have a specific heat of 2, and we set up another object where we have a specific heat of 5. I then want to see what the temperature change is going to be. Oh, and we're going to make our mass easy. We're going to give ourselves a mass of 1 gram because it'll make the math nice and easy. And we're going to say we have a heat flow of 10 joules. So, in scenario 1 here, I have 10 joules. I have my mass of 1 gram. And I have a specific heat of 2 joules per gram per Kelvin. So my temperature change allowed here would be, my grams would cancel out, 10 joules divided by 2 joules times 1 Kelvin. So my temperature change would be 5 Kelvin if I have a specific heat of 2. But if I have a specific heat of 5, and I use that same 10 joules and only 1 gram of my substance, there, my delta T could only be 2 Kelvin. So as I increase my specific heat, I decrease my change in temperature. I love those type of games. Therefore, for the same amount of heat added, what will occur in a substance with a lower specific heat? A greater increase in temperature. In other words, specific heat and temperature change are inversely related. And that's where I actually want to stop for this slide. I don't want to do this. We'll get to that type of question later. That's all I want to on that learning check. Let's move on. All right, example time, example time, example time. Get your pictures and your pages and do another example with me. Before I open my big mouth and work this, pause me and try it yourself, please. All right, I hope there was an awkward pause there. No, you're comfortable with silence? Then I envy you. All right, let's take a look at this problem. A hot water bottle contains 750 grams of water at 65 degrees Celsius. If the water cools to body temperature, how many calories of heat would be transferred to the sore muscles? All right, we see that we have a temperature change, right? At 65 degrees, and it's cooling to 37. That's our clue. We see a temperature change. So that's our clue. Our specific heat formula is going to come into play. They gave us in the problem a mass, 750 grams. I'm going through just like with gas laws and labeling my variables. They gave me a temperature final, and this is a tricky one, right? We're starting at 65, so that's our temperature initial. We're cooling to 37. So that's actually our temperature final. So we want 37 degrees Celsius minus 65 degrees Celsius. We're wanting to solve for the quantity of heat. We need our specific heat though. Hey, wait, we're using water, right? A hot water bottle contains water. Well, you've memorized that the specific heat of water is 1 calorie per gram per Kelvin or per degree Celsius. So now we have everything we need to plug and chug. And I'm hoping you work this on your own and you're going to get an answer that's going to startle and amaze you. We have Q equals 750 grams times 1 calorie. And we're going to treat that 1 calorie like an exact number. Times 37 degrees Celsius minus 65 degrees Celsius. A lot of you are already bothered by that, I hope. We've got 37 minus 65. The answer to that is a negative 28. You need to leave it as a negative quantity, and we'll talk about that here at the end of the example. So we've got a negative 28 times 750. That gives us a device that's not working. It gives us a negative 2.1 times 10 to the fourth calories. What about this negative sign? We've talked about negative signs in thermodynamics before when we were looking at our electrons. In thermodynamics, negative sign means our system, or what we're interested in, is losing energy. And we know this, right? Why do we know this? Because our water is cooling. In order for something to cool, it has to lose energy. So our hot water bottle is losing energy, so we'd expect that energy change to be negative. That having been said, your book is Satan's spawn when it comes to positive and negative signs. You have to be very careful with the wording of some of these problems and how they're wording it. If they asked for just asked for the change of heat of the water bottle, the answer would be a negative 2.1 times 10 to the fourth calories. However, they used words to tell you that the hot water bottle is losing energy. They're telling you how many heat could be transferred to the muscle, right? They're telling you how many calories of heat could be transferred to the water muscles. They're already letting you know that the system is losing heat or transferring heat out. Because they're already implying the direction of heat flow with the question, it's most likely that mastering chemistry in this scenario would just want 2.1 times 10 to the fourth calories. If this was a test question in an in-class setting, I would probably take both answers under this scenario. When you're doing a homework problem, read the question carefully to detect which way they're wanting it, whether they're asking you a change or whether they're already telling you the direction of the change. Fun with algebra! Let's take a look at this one. What is the specific heat of a metal if 24.8 grams absorbs 65.7 calories of energy and the temperature rises from 20.2 Celsius to 24.5 Celsius? Try it yourself and pause me. Okay. So let's take a look here. We see that there's a temperature change. So right away, because we see that temperature change, that's our clue that we're using a specific heat formula. Whenever you see a temperature change, use that specific heat formula. Here's what's unique about this example. This time, they're giving you the quantity of energy. They're giving you the mass. They're giving you the change in temperature. What they're not giving you is the specific heat. So your specific heat is actually the variable you're wanting to solve for in this equation. So let's do some quick algebra. First, we'll start with the monkey in the middle. I actually messed this example up in class once because I couldn't subtract. So now I'm double checking my subtraction. I can do it today. Yay, me. All right. So now we've got 65.7 calories divided by 4.3 degrees Celsius divided by 24.8 grams equals my specific heat. How did I do that? I have to get my variable by myself, so I divided both sides by the things I needed to get rid of, yes? So I've got 65.7 divide by 4.3 divide by 24.8 equals, whoops, equals 0.61609 sig fig check. I hate specific sig, depending on the grad students, these things can be really bad in terms of sig figs. You'll notice our subtraction step does reduce us to 2 sig figs. So really our best answer here would be 0.62. Chemistry's easy, life is hard, unless you're Captain Boomerang. Captain Boomerang. Captain Boomerang. Do I need to say what to do? A rose by any other name would still be the Ninth Doctor's companion. Synonyms and tweaks to specific heat. There are a couple quantities out there that are essentially identical to specific heat. However, their units or just their names may wind up throwing you when they don't need to. The first of these is heat capacity. Heat capacity is the amount of heat required to raise the temperature of a given object or substance. The difference between heat capacity and specific heat is specific heat's always relative to 1 gram. Heat capacity is specific to a given object. In other words, I could pass you my baseball and I could say, figure out the heat capacity of this baseball, or figure out the amount of heat it takes to raise the temperature of this baseball by 1 gram. So heat capacity is the amount of heat required to raise the temperature of a given object. Now, its formula is a little bit catty. Get it? Get it? Get it? Catty? Here, because mass is irrelevant, because we're talking about one object, your heat is simply equal to the heat capacity times the change in temperature. Your hint that you're going to use a heat capacity is you're going to see a change in temperature, but there's not going to be a mass given for an object. Specific heat will also generally have, I should have put in units, will generally have units of joules per Kelvin or joules per degree Celsius, or sometimes they'll be really evil and give you kilojoules per Kelvin or kilojoules per degree Celsius. But you'll notice from the units for heat capacity, the mass term is missing. Another thing that's essentially the same as specific heat, except that it's not, and this is one your book likes to use, is molar heat capacity. Molar heat capacity is the same thing as specific heat, except instead of being per 1 gram, molar heat capacity is, guess what? I'll give you 3 guesses and the first 2 don't count. Molar heat capacity is per 1 mole. In other words, it's the amount of heat required to raise the temperature of 1 mole of a substance by 1 degree Celsius. Its formula is essentially going to be identical to that of specific heat. I would write it Q equals N to the C to the delta T. In other words, you've got several cats. Your clue really for this one is evil. And that's why I have the danger, Will Robinson. Danger, danger, danger. The reason molar heat capacity is evil is they will often give you grams in the formula. However, what you're going to see is you'll see that your constant, instead of having those nice cheerful joules per gram per degree Celsius, your units will be joules or kilojoules even per mole per Kelvin. Don't mind the gap, instead mind the units. Watch out for those units. That's really the only warning you'll get that you're using molar heat capacity, is that you'll see units of joules per mole per Kelvin. I will get students on the message boards during the semester in tears saying they've worked the problem a million times. They'll send me a photograph of what they've done, and they've done everything perfectly, except they didn't notice that they were given molar heat capacity instead of specific heat. So watch for those units. They don't really jump up and down and say, hey, 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 you were using molar heat capacity. Always mind the units. Let's work it! The molar heat capacity of water is 73.1 joules per mole Kelvin. How many kilojoules would it take to raise the temperature of 1.412 kilograms of water by 10 degrees Celsius? Well, we see a change in temperature. We're going to raise the temperature. So right away we're thinking specific heat. Then we notice they give us a molar heat capacity. See, we see the units there of moles. So we know we're going to have to modify that formula just a little bit. Q equals N times our molar heat capacity times our change in temperature. We're going to solve for the Q. We need an N. Where are we going to get N? Well, they gave us a mass. And hopefully by now, you're doing unit conversions between mass and number of moles in your sleep. Hopefully everybody else around you who listens to these is also doing them in their sleep. 1 kilogram is 10 to the third grams. Then we know that 18.00 grams of water is equal to 1 mole of water. Where did that come from? Where did that come from? That came from the periodic table. And remember, we're pushed for time here, so I'm not going to show you how to get off the periodic table again. You should know how to do that at this point in the semester. We've got 1.42 times 1,000 divided by 18 equals 78.9. And that's a lot of moles. Wow. Wowzer, Scoob. So now we have 78.9 moles at a cost of 73.1 joules per mole Kelvin times a temperature change of 10 degrees. So 10 times 73 times 78.9 times 73.1 times 10 gives us a heat of 5.767 times 10 to the fourth joules. I'm going to clean it up a bit, plus they asked for units of kilojoules. So that gives us 57.6 kilojoules. There you go. Mind the units. One more quick example. You can tell this is mine. There goes the grammar right off the bat. A styrofoam cup has a heat capacity of 3.39 joules per Kelvin. If a styrofoam cup initially at 23.4 degrees Celsius absorbs 38.3 joules of heat, what is the final temperature of the cup? Whoa! All right. Well, we see that we're undergoing a temperature change. So that's a clue that we're going to be using one of our heat formulas. We see that we're given a heat capacity with units of joules per Kelvin. So that's how we know we're going to use our heat capacity formula. Q equals C delta T. I gave you in the problem the quantity of heat, 38.3 joules. I gave you the molar heat capacity. I want to solve for the final temperature. Here is a word of advice. You're not always going to be able to do it, but if you're allowed to algebraically avoid breaking up that delta T until the last step if you're wanting to solve for one of your temperatures. Now we know that that delta T is going to be whatever temperature final we arrive at minus the initial temperature of 23.4 degrees Celsius. But I don't want to break that up into individual pieces until the very last step. If I wanted to, another way to look at it would be 38.3 joules equals 3.39 joules per Kelvin times TF minus 23.4 degrees Celsius. Instead of distributing my 3.39, it's a lot easier in life if I just go ahead and get rid of it right now. When I do that, I get 38.3 divide by 3.39 equals 11.3 Kelvin is equal to my temperature final minus 23.4 degrees Celsius. Remember, this is a change in temperature, so we can just go ahead and slide in that degrees Celsius right there if we want to. Now I have to solve for my TF, so I'm going to add 23.4 to both sides to get my TF by itself. The algebra starting in this chapter really begins to kick it up a notch, by the way. 23.4 degrees Celsius, and that gives you (34.7 degrees Celsius as your final temperature. Ta-da! Chemistry is easy, life is hard.